All right, good morning. How is everyone?
Doing all right, Nick. How are you doing?
Doing all right too, thanks. I'm glad it's Friday.
Me too.
All right, so let's talk about homework 8. So my original suggestion was that even though homework 8's not due until Monday morning, I suggested to treat the due date as today at 8 a.m. The reason being that, um, if you finish it by this morning at 8 and submit it, you're done. You don't have to worry about it after that. Um, but then if, you think you're done and you do your final tests and you discover something's wrong and you can't fix it, and you work Thursday night and you're trying and you can't figure out what the problem is, then you can ask about it in class today, which is right now. And if that doesn't work, you can still come to office hours at 2 and share your screen and show me your code and show me your tests and so on, and we can figure it out. And then by, the end of office hours today, you'd be done. And you submit it, you don't have to worry about it again. So I was hoping that, everybody would have it submitted and finished by this morning at 8. And I went to download and there were 20 or so submissions on Git. So there's two ways I can interpret that. One, people just haven't, tried to get it done by Friday at 8, which is fine. That's your time management decision. Or two, that, half the class plus is in some sort of dire strait. There's some problem you can't solve, and you're not sure what to do about it. So if that's the case, right, let's talk about homework 8. Either right now or catch me in office hours at 2. And let's work out whatever the details are, and make sure homework 8's working perfectly for you. I'm not going to be helping people online over the weekend on this assignment, so ask in class right now, or come to office hours at 2. Whatever there is that's not quite right. Leading spaces, strange characters, counts that just aren't making sense, how to input from a file, how to run against test cases. What can I help you with? All right, let's see. I ran the test 4 and checked if there are differences. Everything was good, but one line was different. The line had 2 numbers and a $sign. My version of the program basically removed the numbers and the $sign. Yes. So $signs can sometimes be treated as a funny character, depending on what you do with them. And I don't think I've been able to successfully reproduce that problem. But typically, you have some kind of line like this. And if you use that in certain ways, these $1, $5 will be interpreted as variables whose value should be replaced. And my only suggestion is break things into steps, right? So this comes up, for example, if you try to do something like, tally bracket $phrase equals $curly bracket tally bracket phrase +1. I think this will get you into trouble. because this phrase contains $1 and $5, and I think those will be replaced with, the first and fifth arguments to your script inside this evaluation, and I think that munges them down to empty strings. So instead of doing this, right, do something like, value equals, and put your phrase inside quotes, right? Get that value, increment it, and then do a reassignment back into the array. And so someone says they ran into that problem a few days ago. Did you have a quick fix that ultimately resolved it? Or a clear fix?
Yeah, in order to fix it, I ended up having to initialize the tally value.
Oh, that's right. I remember that.
And we figured out it had something to do with how it incremented it, the associative array.
Right.
So caused the problem, the double parentheses.
Right. Okay. So yeah, try doing something like this, and throw in some debugs, right? Echo your phrase beforehand, throw it in delimiter, square brackets, angle brackets, something, so you can see exactly what the phrase looks like. And this should preserve the dollar signs, and then do this and see what your value looks like, and so on and so forth. Called it line. All right. So that should store store the line under, store the value 1 under that line. Let's double check and make sure. So let's do our funny iteration. Right. So those dollar signs are not getting consumed. Let's say the same issue. Your first example should work as long as the phrase is in quotes. The problem happened when the key was only set inside a math operator. So yeah, so if someone did paren tally bracket $ phrase plus equals 1, that seemed to do that also. So I'm curious, if we don't use quotation marks, I think this may still work. Yeah, so that's still use the same value. So let's see if we can break this. So $, paren, paren. $, curly, tally bracket, $, line, +1. That still seems to work. Interesting. So I don't have a solid explanation for why this happens, but it appears, unless there was a typo in here, it appears that these $signs do get consumed unless you already have an entry in the associative array with, you know, that exact combination of characters, which is happening when you initialize the array to 0. And for some reason, when it's gobbling up these $signs and interpreting them, it seems to look in the array first. And if you already have an entry with this key, then it seems to preserve those $signs. That sounds really weird, but that seems to be what we're seeing here, and that also goes along with what some other people have reported, where by initializing the entry in the array, they were able to preserve those $signs. But you can definitely avoid that by doing it like this, by first reading the value out and then incrementing it separately and then writing the value back in. The mysterious part is that if you do this, sometimes it preserves the $sign, sometimes it doesn't. But that falls in the realm of so many things in Bash, which is I learn how to do something I need to in Bash, and I don't spend too much time trying to understand what other things mean to Bash. Just because I don't really have the bandwidth to learn everything there is in Bash, and there's so many different ways to do things. But if you have time and if you want to become, you know, more of an expert in Bash, these are really good things to dig into. And I'd love to know what exactly is happening in this case. But for homework 8, just split it into 3 steps: read, modify, write. All right, other questions? Leading spaces, how to get rid of them? So let's say this is our line. If you just echo $line, it looks okay. Right, it looks like exactly what we would like. My suggestion, first of all, when you're debugging, put in good debug statements. Don't just echo your variables. Echo something like, you know, before cleaning, line equals, and let's put in a delimiter, like square brackets. Let's put the whole thing in quotes. And now when I'm running my script, I'm going to get a message which says, before cleaning, the line is equal to, and I can see really clearly there's, you know, spaces before, there's spaces after. And then, you know, go ahead and remove the spaces. Okay, so sed, for example, if I say sed, look for, at the beginning of the line, 0 or more spaces. So an asterisk means 0 or more of the thing before it. The thing before it is a space. So this pattern will match 0 or more spaces at the start of a line, and I want to replace them with nothing. So if I do that and there's no spaces in the start, nothing happens. If there's a single space, it gets removed. If there's a bunch of spaces, they all get removed. If there's other spaces in the line, they're left alone. All right, so that's how you play with these things from the command line, and you say, okay, it looks like this will get rid of leading spaces. Now, how do we use that to clean up a line that's stored in a variable? Echo your line and pipe that into sed. Right, and there we've gotten rid of the leading spaces. And then if we want to save that in a variable, let's just set a new variable, call it line 2, set it equal to, you know, all of that stuff inside back quotes. And now if I echo line 2, right, I've gotten rid of those leading spaces. All right, so there's trailing spaces at the end. Let's echo line 2. Let's save it as line 3. So what's a trailing space? It's 0 or more spaces, so space followed by an asterisk, followed by the end of the line. So the $sign says this pattern has to be anchored to the end of the line. So if I do this, take the line that has trailing spaces, run it through sed, substitute any number of spaces at the end of the line with nothing, and then take a look at line 3. Line 3 is nice and clean now. So that gets rid of leading, that gets rid of trailing. And you could also do something like string your seds together. So output the original line, run it through a sed that removes the leading spaces, take the output of that, run it through a sed that removes the trailing spaces. Run it through something that changes case. Let's run it through something that changes all the spaces to underscores. And you can keep chaining these things together, you know, however much you like. And then, you know, you've got your cleaned up input. But when you're developing your code, sometimes it's nicer to do it in steps like this, because then you can look at the value after each execution, and that can help you find, you know, where something's going wrong. If I do all of this and my clean line ends up empty, I made a mistake somewhere in one of these things, but it's a little hard to figure out where that is. Sed quote substitute slash bracket backslash s backslash t close bracket plus slash space g. What does the backslash s do? Is that a space? That should replace all spaces and tabs with a single space, I believe. But it's not going to compress multiple spaces. Oh no, that should. Okay, so backslash s looks like a space. The G replaces them globally. If you do a plus, it should do one or more of those. But that doesn't seem to work. Interesting. I'm not sure what the problem is there. It may be, um, that the backslashes on the S and T are somehow confusing the grouping in the brackets. Because that's... Alright, I'm not very good with the plus, so I would do it as a space, and then a space star. Right, so if you do a space followed by a space followed by an asterisk, that says a space followed by 0 or more other spaces. If you just do a space followed by an asterisk, that technically matches everything in your input, because everything is, you know, a succession of 0 spaces. So yeah, I've never used plus in regex. I know it's a thing, and I think it's supposed to do the same thing as star, but it says 1 or more. But I've just never played with it. You could put the \s\t in quotes, but I think inside the single quotes outside it would end up looking for a quotation mark. Let's see, it was really convenient it wasn't due today because my main computer had internet issues 2 days ago and I was only able to fix it yesterday night. Alright, good timing then. Cool. Let's see, substitute \s star \t star. Does that work? Interesting. I've never put stars inside brackets either. Regexes are always a bit of a mystery, to me at least. But again, you know, back to the adage I keep coming back to, figure out how to do what you need to do, you know, in a way that works for you, and get really good with that, right? All right, good. What else? Other homework 8 stuff. Alright, well, if something occurs to you during class, go ahead and ask it. And if not, go ahead and hop into office hours if you still have questions, 2 o'clock. And we will we'll figure out what's going on. Alright, so let's go back to looking at process creation. So we played around with the fork command yesterday. I want to do this a little more deliberately. So fork is a function call we can make from C. And if you look at the manual pages, fork is in chapter 2. All right. So, you know, the manual pages are broken into 8 chapters. Chapter 1 are basically commands you would run from the command line. So, you know, date and GCC and things like that. Chapter 3 are usually the things that we would call from, say, a C program to do the kinds of stuff C programmers do. So printf, fgets, fopen, fclose, things like that. Those are chapter 3 commands. Chapter 2 contains the lower level commands, sort of the system level commands. So binary I/O, open, read, write, close, and also fork. Okay, so this is kind of a system level operation. It's not something we would typically use if we were writing a high-low game, right? But if we were writing, you know, some sort of system level process, we might want to use this. So this is lower level stuff. And the way we work with fork is pretty straightforward. You basically call fork, and this creates a clone of the current process. And it returns effectively, you know, an int, which I'll just call R. And after this call executes, you now have two processes. You have an original and you have an almost exact copy. Okay, now what's the problem with making an absolute exact 100% perfect copy of a process? The problem is the copy doesn't know that it's the copy. And so it's going to try to go to your job, and it's going to try to take your exam for you, and it's going to try to eat your food from the refrigerator, and so on and so forth, right? So, and if you say stop that, you're just a clone, it's going to say no, you're a clone, right? So how do you know which is the original process and which is the copy? You got to have some kind of marker, all right? So there's an old sci-fi movie where if you looked inside the eyelid, there'd be little dots tattooed to indicate what generation of clone this thing was. So same idea with a fork. With a fork, the tattoo that tells us that the process is a clone is this return value from fork. So for the original process, which we call the parent, R is equal to the process ID of the clone, which we call the child. For the clone, child, R is equal to 0. And that's the only difference. So you write a C program, you're assigning values to variables, all kinds of stuff, and then at some point you make a call to fork. And somewhere inside this call, something happens. A new process is created. And that process looks exactly like the original process. But when you return from that call, you've now got two processes executing code. They're both at this point in their program where they're saying, okay, let's take the return value from fork and save that in this variable. One of them is going to save a 0, the other one's going to save something non-zero. That's the only difference. But from there, we can differentiate into whatever we want the two processes to do. So let's make some code. So we need to include a few things. Alright, so we'll store my password in a variable. Oops, I shouldn't have told you my password. And I'll have an integer for a return value, and let's just print out a message. Say I'm ready to call the fork method. And then we'll go ahead and we'll call fork, and then we'll print out a message. And we'll print out the value of I, and we'll print out the value of retval. And then we'll just exit. Alright, so what's going to happen here? We're going to initialize a variable to a number, we're going to make a call to fork, and we're going to save the return value from fork in a variable, and then we're going to go ahead and we're going to print out the value of that first integer I, and then the value of retval. Is there an all.h? Where would you want to use it? What would all.h be? You mean like something that includes everything? No, I don't think there is. You could make one if you had, 10 things that you tended to include a lot. You could make a Uber include file that includes each of those. But there's some conflict potentially between some of these .h's. And if you included everything, you'd end up with a huge amount of extra stuff to deal with in your compilation. So you usually want to be pretty tactical about what you include. But sometimes you're working on a particular thing, and so you always include the same 15 files, and you might want to just go ahead and put those inside one big include. Thanks for the quote. Alright, so let's run F3. So it was ready to call a fork. It came back from the call to fork and reported I was still 12345, and the return value was 2289. And then we got a second message. This was coming from a totally separate process, right? A clone of the original process, which had the same value of I, but had a different value for what came back from the call to fork. The fact that this was a 0 tells you that this print message came from the child process. Alright, so if we sleep at the end of this before we exit, and I run this in the background, I can look at this and I can see what's going on. There's my bash shell, right? Process ID 869. Process 869 is the parent of this command F3 that I executed by typing F3. That's process ID 2310, which is the parent of another version of F3, which is 2312. And then this is just the PS that I ran. So why was the first one 2289? I don't know where 2289 is. So the original bash process was 25869. And that created a process 2310, which created a process 2312. Which would have been awesome if that was 2112. But I don't know where 2289 is coming from. I don't see that. How do we communicate between the parent and the child? So that's a really good question. So retval number 1 was 2312. Oh, up here. Because that happened to be the process ID that was assigned to the newly created child, was 2289. These process IDs are more or less sequential. So between that and this call to F1, a number of things had happened. And the next available process ID was 2312. And so that's what got assigned to the child here. And if I run this again, right, now the child ID is created with child's created with process ID 2383. And this is like doing PS a bunch of times. Each time you do this, you get a different process ID for the PS command. That jumped by 10 there, but then I typed quickly. Alright, so someone said, how do we communicate between the parent and the child? That's a really good question. We can pass information to the child before it's created. Right? Any variables that we have in the original process, like the value of I, those will be available, those will be inherited by the child process. But once we've created this child process, so here's the original. and we set I equal to 1, 2, 3, 4, 5, and now we do a fork, and so this has a copy of I as 1, 2, 3, 4, 5. Now if I set I equal to 0 over here, that's not going to have any effect on the value of I in the child, because they are independent processes at that point. But what we can do is, before we make this fork, we can set up a conduit that lets these two processes communicate. And what we're going to do is we're going to set up a pipe. We're going to create two file descriptors that are connected by a pipe. So maybe this is file descriptor 4 and 5. And then after the fork, we've got a pipe here with descriptors 4 and 5, and the child process has the same pipe. And the way this pipe is set up, anytime I write into this end, it comes out that end. Well, since this child has a clone of the original process's pipe, if I write into this end, it's also coming out of this end. And so the child can read messages from the parent by having the parent simply write them into one end of this pipe, and the child reading them out of the other end. And if I want to have two-way communication,
Make the video stop working.
say again?
We have lost your video.
Oh, really?
Your Zoom cut out and then it reconnected you, and now we can't see your video. You're
Oh,
just fine though.
how's that?
That's good. Thank you.
I wonder why that happened. How long was it out?
Probably about 20, 30 seconds.
Interesting. Okay. Mysteries of Zoom. I'm pretty sure my internet's being wonky today. I was pretty close to driving over to Clark because I thought I wasn't going to be able to get connected this morning. So we'll see if it holds up. All right. So so yeah, you can create this pipeline, and when you clone your process, both the original and the child process have this pipeline. And if the parent writes into one end, the parent could read from the other end, but the child can also read from that other end. So that gives you a message passing mechanism from parent to child. And then you can create another pipeline and have that be cloned as well. But set that up so that you write into this end, you can read from this end, and so you let the child write into that end, parent reads from this end, so now you have two-way communication. And we're going to actually set that up later on, possibly next week. All right, let me get my chat window back. So any chats that happened recently I don't have, because the chat window seems to clear out when I start screen share. All right, but that's how we can communicate between processes. All right, so there's a simple example of process creation. Okay, using a call to fork. So we can capture that return value and do something like this. Right, so make your call to fork and then check the return value. If it returned a 0, you know you're the child process. If it didn't return a 0, you know that you're the parent process, and you also know the process ID of the child, because that's what got sent to you in return value. It's a Friday. All right. So we do that, right? The parent identified itself, told us the ID of the child, and then the child just said, I'm the child process. Right, and so there's the processes. All right, so the thing we said not to do yesterday is this. All right, so this is a small fork bomb. Each time that we execute this series of instructions, the number of processes will double. Because each process is going to, we're going to start off with one process that's going to fork. We're going to have a process and a clone. And then both of those will go back up here and execute a fork. So each of those will create a child process and so on. And so lots of process creation taking place. Lots of children, lots of parents, and lots of processes. All right, so again, don't do that on the Linux server. Don't do that. Don't call fork a bunch of times recklessly. If I made this, 20, my machine would crash because I would try to create 1,000,000 processes and I would run out of resources. And you're dealing with very low-level resources. There's things called process slots. Every time a process is created, you need to know a lot of information about it, and it takes memory to store all that information. Remember, on a single core machine, only one process runs at a time. So if your process is running and it's time for another process to run, all the information about your process has to get saved somewhere, and that takes memory. Right, so the more processes you have, the more resources are consumed. And if I looped 20 times and tried to make 1,000,000 processes, there's not enough memory on the system. There's not enough space in the data structures to store that information, and the system will at least grind to a halt, but probably crash outright. But if you're virtualized and you want to try that on your own virtual box, go for it. It's fun to do. All right, so this is what happens underneath when a process is created. And we may not always call fork ourselves, but ultimately, anytime a new process is created, something is probably calling fork at some level. But there's other ways to create processes. And so one really nice command is system. So I'm going to print out the date is, then I'm going to run this command system, and I'm going to pass it the string date. And then I'm going to print out goodbye. All right, so it says the date is, and then it shows the output of the date command. And then it says goodbye. So system is a chapter 3 function. It's something that's considered higher level. And we should include standard lib to prototype it properly and so on. I'm being sloppy. But system basically lets you pass in the name of a command. And we'll execute that. First, it will use fork to create a child process. So system does a few things. It creates a new child process. And then it does something called an exec. And it does that to execute whatever command you pass to it. And it executes it with the command sh. Okay, that's the Bourne shell. It's slightly different from bash. But it's another shell. And then when the command finishes executing, system returns. So let's make this a little more interesting. Let's put a sleep in there. Alright, so not much running on my system right now. Let's go ahead and run this in the background. And let's do the PS. And you can see there's 3 new things happening here. There's the command F4, okay, which was created from bash, and that's process 3411. Well, that's running because I said F4. So that's the program that I started from the command line. That process 3411 is the parent of another process 3412. What's that process? sh-c date. So that process is trying to run the shell sh with a switch -c, which says I'm giving you a command on the command line, and the command is date. And then it's executing a sleep of 60 seconds. So this date semicolon sleep 60 was passed as a command line argument to the function the program sh. And that program 3412 created yet another process to execute the sleep. Alright, so processes create processes. This is how things are set up in Unix. And this was created by using a fork. And this was created by using a fork. But for us, you know, and you can see after 60 seconds, my sleep expired, and my main program F4 continued, and it printed out goodbye. And if I do a PS again, you can see those other processes have gone away. Right? So this is a really powerful thing we can do. Just calling system. And you can put in more or less any command, but you've got to be, you know, somewhat reasonable. Let's say I want to execute VI from the system command. That's probably going to upset it. Well, no, it's actually not. That worked great. Alright, so system is fairly robust. And you can introspect with this. If you want to know what directory your command is being run from, let's just run the system command to execute pwd. And it shows me, you know, this is my current directory, so it's running it from the directory I happen to be executing my program from. Alright, so system's a nice, quick, and dirty way to just execute a Linux command, but it's somewhat limited. It makes it a little hard to capture the output. It makes it impossible to send input to the command you're running. It's really just for executing something. So we'll dig further into fork, and we'll start playing around with exec to actually do more detailed control. We're also going to talk about something called popen, and that's going to force us to talk about file IO first. So we'll start with that on Monday. All right, cool. Have a great afternoon. I will see you next time. Thanks.